Welcome, everyone. We'll get started in just a few moments. Okay. Hello, everybody, and welcome to today's AEESP webinar supported by sustaining member Dynamita. Introduction to Activated Sludge Processing Modeling. Process modeling using SUMO. I know that we are all eager to get started with the presentation, but I have a couple of quick housekeeping items before we do. We will be taking all questions today at the end of the webinar. That being said, please feel free to ask your questions at any time during the session using that Q&A section located in the bottom toolbar, and it's shown on this slide. A reminder to everybody that you will receive the webinar recording and slide deck after today's session. So thank you again to AEESP sustaining member Dynamita, and without further ado, I will hand things over to our moderator, AEESP President Cara Nelson. Cara, please take it away.
Thank you so much, Erica. I'd like to begin by welcoming everyone. So I am a professor at UC Berkeley in environmental engineering, and I am very honored to be the president of the Association of Environmental Engineering and Science Professors this year. This is our third sustaining member webinar, and these webinars are a new program that we believe are of great benefit to our members and our broader community, and they are free to attend, and you do not have to be an AEESP member in order to participate. So if you're joining today and you're not familiar with AEESP, I want to share that we are a diverse and inclusive community of over 1,400 members, which include educators, researchers, and graduate students. And then we have a special membership category for companies and organizations who can join as sustaining members. So Dynamita is one of our valued sustaining members. A little bit more about AEESP. We are an organization that is run by volunteers, and we have a wide range of activities and programs that aim to support the professional development of our members, and that also aim to evolve our field to address the grand challenges of today and the future. So if you would like to learn more, you can learn a lot more on our website, aeesp.org. You can also search for us on LinkedIn, or you can send me an email, and my email is on our website. And if you are not already a member, then I would encourage you to consider joining. So with that brief introduction to our organization and what got us here today, I'm now going to introduce our speaker, Dr. Tanush Wadhawan. Dr. Wadhawan received his PhD from North Dakota State University, and then he spent 2 years at DC Water before joining Dynamita. And he has been a process modeling expert and is now the director of the North American operations with Dynamita, where he's been for over 10 years. So we're really looking forward to your talk today, and I will hand things over to you, Tanush.
Thank you, Cara. And thank you, Erica, for helping in organizing this session. Okay, guys, so let's begin. So today I'm going to introduce you to activated sludge process modeling using SUMO. I'm going to try to balance between some of the beginner, intermediary, and some of the advanced information. And of course, if you have any questions, feel free to write it in the Q&A. So what are we going to achieve today? So we are going to actually try to build an activated sludge plant in our software SUMO. We'll look at calculating yield or sludge production. We'll look at calculating the total aeration demand of the plant. We'll try to understand the impact of sludge retention time, SRT, on nitrification, specifically at low temperature. Then we'll upgrade the plant, a simple single CSTR plant, into a plug flow activated sludge system. We'll reevaluate the impact of SRT on nitrification performance, on the total aeration demand. Then we'll further upgrade the plug flow activated sludge plant into an MLE process for nitrogen removal. Then we'll look at the impact on our SRT, on nitrification performance, our denitrification, and evaluate some of the operational and design parameters. And finally, once we have done looking at different configurations in SUMO, we'll come back and I'll try to link how the model matrix links to the process operation, how you can look at rate equations and understand what will impact your process. Okay, so let's begin. I want you to understand three important categories when we are looking at a wastewater treatment facility. The first category is understanding your influent. The whole point of your wastewater treatment plant is to treat your influent, of course. So understanding your flows, your loads, the characteristics, such as how much is biodegradable, how much is unbiodegradable, what fraction of your COD might be soluble, how much might be particulate. So understanding your flows, your loads, your characteristics, and temperature of your influent is very, very critical. The second category, which I like to look at, is operations or engineering inputs. So understanding the volumes of your different process units which you have in the facility. Understanding the configuration. If you have step feed, you have anoxic zones up front. If you have anaerobic zone up front, then understanding the configuration of your plant is very, very critical. And then comes some of the design or operational parameters, such as what is the sludge retention time of your facility? What are the dissolved oxygen set points or your airflow rate in your aerobic tanks? What is your internal recycle if you have an MLE kind of facility, or other recycle rates or return from your dewatering facility, for example? Are you adding carbon? Are you adding chemical? So understanding the operation requires you to understand some of these different objectives. And finally, looking at the performance criteria. So how do you evaluate the performance of your plant? Of course, you look at the sludge production, you look at the oxygen demand, you look at the effluent quality, and then you look at removal efficiencies, right? So these are the things you do at minimum you need to do to kind of be able to understand, develop a model, and evaluate your process performance. All right. So at this point, we'll actually directly jump into SUMO. So I'm gonna bring up SUMO. So the first time you open SUMO, this is the first screen you'll see, and this is called the home screen. In the home screen, you'll find at the bottom, there are many different examples you can choose from, such as a hydraulic SRT example, a tutorial plant example, which is a simple activated sludge plant with primary treatment, and then you have some advanced configurations as well. You can walk through different examples if you want to set up a particular configuration. So today our goal is to set up an activated sludge plant. So what we will do, we will just go into our configure tab, and this is where you get to build an activated sludge plant. So what you see on your screen is the drawing board. So I'm going to drag and drop process units from the left-hand side of the screen onto the drawing board and try to build a simple activated sludge plant. So the first thing we need to do is go to our flow elements, click on the influent and drag it to the right. And then because I want there to be primary treatment, I'm going to go to separators, look for my primary clarifier, and drag that to the right as well. Okay, what else do I need? I need a single CSTR. So I'm going to go to a CSTR, drag that to the right. I'm going to do the same thing for a secondary clarifier. I'm going to go to solid liquid phase separators and then drag my clarifier. All right. So these are some of the essential units you need to be able to set up a configuration. Apart from that, we want to bring the RAS back to the head of the CSTR. So I'm going to bring back a divider and a combiner in a moment. But let's see how we connect the influent to the primary influent port. So I'm going to click on my output port of my influent. Without leaving this red line, I'm going to bring it close to each other. And you can see now I'm telling SUMO that the influent flows into your primary clarifier. In a similar way, I can send the effluent of the primary clarifier to the influent input of the CSTR. Now, but before I do that, I'm going to right click and disconnect. And I'm going to place a combiner because I want the return activated sludge to come back to the head of the plant. So I'm going to make this connection right here. I'm going to right click on this combiner, do mirror up down. So I flip the combiner, and then I'm going to send the effluent of the CSTR into the clarifier. I'm going to go back to the flow elements and drag a side flow divider. And a divider will allow me to set up wastage from the activated sludge system. So I'm going to just turn this around, bring the RAS or the underflow of the clarifier to the input of the side flow divider. And then I'm going to get the overflow to go back to the head of the plant. All right. Now I can attach an effluent to the secondary clarifier, and I can combine the sludge from my primary underflow of my primary clarifier and my wastage into a single sludge unit. All right, so this is the simplest configuration one can create for activated sludge system. So to go over this again, I have influent going into my primary clarifier. From my the primary effluent goes into my CSTR, then into a clarifier, and then the return line or the RAS or the underflow of my secondary clarifier goes back to the head of the CSTR. And before it goes back, it gives me an option of wasting the sludge so I can control the sludge retention time. Okay. All right. One important aspect which I would like everyone to understand is in the configure tab, we have so many different process units or so many different units which you can create any number of configurations from. So let's click on the CSTR. You can see that I have highlighted the CSTR, and on the left hand side, I have more options which I can select from, which will allow me to select different type of models. To learn more about the type of models we have, you can visit our website. For now, I'm going to choose an input dissolved oxygen CSTR with diffused aeration with ceramic membrane diffusers. Next, I'm going to go to the model tab. But before I move on, I'm going to save this configuration as activated sludge plant number 1. And in the model tab, you'll see that you get to select different type of model options we have. So the first option is the type of biokinetic model you can choose. By default, we have one-step nitrification, denitrification model selected. You have an option of selecting two-step nitrification, denitrification model. And as the name suggests, in one-step process or the one-step nitrification process, ammonia converts directly to nitrate from a nitrification perspective. So you don't have nitrite as an intermediate. And then nitrate under anoxic conditions will be converted into nitrogen gas. And that's what the one-step nitrification, denitrification refers to. Two-step nitrification, denitrification model, like the name suggests, ammonia will go to nitrite, nitrite goes to nitrate, and then nitrate comes back to nitrite and then converts into nitrogen gas under denitrifying processes, right? Now, you can choose two-step nitrification, denitrification for low DO operation, for side stream treatment, because you have nitrite as an intermediary. You can simulate deammonification process or NMOX in the model. So for today's demonstration, I'm going to be using SUMO 1, which is the one-step nitrification, denitrification model. At the bottom, you can click on key parameters, and you can identify some of the key biokinetic parameters which are available as part of the model. But then there is a whole list of parameters which can be made available by clicking on show all. Okay. Other type of model selection options which you can take care of in the model tab is such as calculating the off-gas, turning on the pH, calculating the ionic strength and the pH, looking at precipitation reactions. Even PFAS is one of the new things which we have added into the model. So you can turn on PFAS calculation and do a mass balance around a whole facility if you want it. Let's go to the tools. In the tools, I want you to think of calculations or create calculations that are not specific to one particular process unit. So for example, SRT or sludge retention time. Sludge retention time has nothing to do with one single CSTR, but it involves all the tanks you might have in your schematic divided by the mass of solids which are leaving your system, right? So what we're going to do is we're going to click on sludge retention time, and I'm going to drag the CSTR to the numerator, the wastage to the denominator, along with the effluent, because effluent also contains solids which are leaving the system and will have an impact on your total SRT. All right. The second thing I wanted to look at was to calculate your sludge yield. How do you calculate the sludge yield? You can go to calculators, click on advanced. I'm just going to double click, change the name to yield. And then I'm going to drag the wastage pump to the numerator, the effluent of the plant to the numerator, so that the mass of solids which is leaving the system can be used in the calculation. I'm going to get the effluent of the primary clarifier and the effluent of the plant at the bottom. Okay, so now my goal is to select appropriate variables on the left-hand side. So the first, I'm going to go to mass flow based frequently used variables. In this, I'm going to select total suspended solids. So I'm looking at total suspended solids in my numerator for these process units. And then in the denominator, I'm looking at BOD. So the mass of BOD coming in minus the mass of BOD leaving the system. All right. So these are some of the things you can do, along with additional controllers which are included as part of SUMO. You can set up ammonia-based aeration control, DO control, and then some statistics. Let's go to the input tab. In the input tab, you can click on any of the process unit, and then you can provide information regarding that particular process unit. So for example, the flow in million gallons per day is 6.3 mgd per day for this facility. You can define the total COD concentration, TKN concentration, total phosphorus, and control the temperature of the plant. If you click on the influent fractions, then you get to decide what fraction of your total COD is biodegradable, what fraction of your total COD is particulate, and you can make those distinctions by identifying these fractions. If I click on the CSTR directly, you will find that you can specify the number of trains. You can specify the volume per train. So by default, it's 2.6 million gallons. You can define the height of the tank. And if I click on another setting, which is aeration settings, you can decide the DO set point. And the reason it's DO set point as an input, because we chose an input DO model when we were setting up the configurations. Another important calculation which we created, the sludge retention time, is available from the top of the drawing board. So if you click on this equation, SRT, this functionality, you can actually turn on the SRT calculation and control the SRT of the plant just by specifying what the SRT should be. You can control the wastage by identifying what the SRT should be. So what I will do right now is change this to true. And then I can say that this plant is should be operated such that the sludge retention time is 5 days. Now SUMO will figure out what the wastage should be in order to meet that 5-day SRT target. I'm going to go to the output tab. In the output tab, I'm going to start creating some of the tables, or some of the variables which I want to look at. So I'm going to click on the table, click on the influent, and I'm going to drag the frequently used variable to the right-hand side. So you can see that it populated some of the important variables which we want to look at. I can do the same thing for the primary clarifier effluent. So I'm going to click on the effluent of the primary clarifier and drag it to the bottom. Same thing for my CSTR, and then the effluent of the plant. Now, we did create the sludge retention time. We did create yield calculation. So we want to make sure that we follow those variables as well. So I'm going to click on SRT on top, go to other variables. I'm going to drag the SRT to the table and drag the plant-wide to the table as well. And you will see that our yield is part of the plant-wide equation. Okay. Now at this point, I can create some of the time charts, or I can continue to look at some of the other important information. One important information might be regarding the CSTR. So I'm going to click on my CSTR. I'm going to go to operational table right here and drag that to the header. And then it will populate some of the information such as the volume, the DO set point, HRT of the system, oxidation reduction potential, the airflow demand to meet that DO set point of 2 milligram per liter, the actual oxygen requirement, and so on. I'm going to also create a time chart. So I'm going to click on the time chart, and I'm going to click on my effluent, and I'm going to drag ammonia, nitrate, and total nitrogen to the time chart. And I'm going to rename this and call it N in effluent. I'm going to also look at my yield. And again, I'm going to go to the plant-wide, other variables, and drag yield to the time chart. What else should we look at? Maybe the oxygen uptake rate or actual oxygen requirement, AOR. I'm going to click on CSTR, go to my operational, and then drag the actual oxygen requirement for the CSTR. Okay, so these are some of the key things I guess we wanted to look at. I'm going to go to simulate, and I'm going to press steady state. All right, so the simulation is done. If I go to the first table, the SRT was set to 5 days. This is the yield of 0.8 grams suspended solids generated per gram of BOD removed from the system. My total nitrogen is from 34 milligram nitrogen per liter to 21 milligram nitrogen per liter. The difference is because there is ammonia being removed due to synthesis. Ammonia is also being nitrified in the system, and you can see that there is a lot of nitrate in the effluent of the plant, right? So it's a completely nitrifying system, and we are able to do a quick simulation at steady state. Now, let's evaluate the change in SRT. So I can go to my input, I'll click on my sludge retention time, and I'm going to choose the SRT target in the advanced right here. I want to do an analysis. I want to be able to change my SRT within a range and identify a relationship between ammonia and SRT at different temperatures. So I'm going to select my target SRT to be part of the advanced. I'm going to go to my influent and do the same thing for the temperature of the plant. So I'm going to select temperature in the raw influent in the advanced section, and then I'm going to simply go to simulate. All right. Now from here, you can see that I'm able to change the SRT and the temperature to evaluate its impact on the simulation. But what I'm going to do is I'm going to click on this advanced button in SUMO, and then I'm going to analyze. So I'm going to click on the SRT. I'm going to change the SRT of the plant from 3 days to, let's say, 8 days of SRT. And I'm going to do 10 simulations in between. So by going to advanced and going to analyze by highlighting one variable, I'm able to specify what SUMO should do in terms of doing a simulation for identifying the minimum of that particular variable, which is 3 days. And then 8 days is the maximum of the variable which will be simulated. And then I'm going to do 10 simulations in between. All right. And I'm going to do this for a low temperature or winter condition. So let's say the winter condition is 12 degrees Celsius. Now, all I have to do is press steady state. So when I press steady state with one variable selected as an analyze, and when I go to a time chart, you will see that SUMO will convert a time chart into an XY chart. And on the x-axis, I have sludge retention time. And on my y-axis, I still have the same variables which I plotted before, such as total ammonia, total nitrate, and total nitrogen. You can see that it is a completely aerobic system for each of the SRTs. So there is not much total nitrogen change as the SRT changes. However, you can see that the ammonia concentration starts off very high, which is at 3 days of SRT. And as the SRT increases, of course, the nitrification performance increases for the facility as well. And looking at this curve, you can identify at 12 degrees Celsius, what is the minimum SRT a plant should be operated so that it achieves, let's say, 1 milligram nitrogen per liter in the effluent for ammonia. And in this case, it happens to be close to 7.8 days of SRT. So at 12 degrees Celsius in the influent, when you change the SRT from 3 days to 8 days, the plant starts to nitrify. And this is an important correlation to understand whenever we are doing design or whenever we are looking at operation of a facility at low temperature. We can also look at what happens to the yield. So as the sludge retention time increases, the yield, total observed yield for the facility or the sludge production in terms of grams suspended solids divided by gram BOD removed per day decreases in the system. What about the oxygen demand or the actual oxygen demand? Of course, you can see that the actual oxygen demand starts off low. And during this time, only BOD removal is happening because you don't have nitrification going on in this system. And as the SRT increases, so does your oxygen demand in the system. So you can see that with just a few clicks, I managed to identify my variable, which is SRT. I want to change the SRT, do 10 simulations and evaluate its impact on ammonia, its impact on oxygen demand, its impact on, let's say, yield of your facility. Okay. So I'm gonna save this simulation. What I'm also gonna do is I'm gonna save this as activated sludge plant 2. And I'm gonna revisit it by changing the system into a mode plug flow system and evaluate its impact. But before I do that, I'm gonna create a report so that we have something to compare to. So by clicking on the Excel button, SUMO will save this as a report and we'll open it and keep it aside for a moment. All right, in the meantime, let's go to configure. And let's upgrade the facility and make it more plug flow. So to make this more plug flow, I'm gonna make some room to add more reactors. I'm gonna disconnect this pipe. I'm just gonna copy the same CSTR and paste it multiple times right here. So I'm gonna make it more plug flow by having 4 aerobic tanks. What I'm also going to do is this time I'm going to add a provision to return some of the nitrified mixed liquor to the head of the CSTR, so that when we go over to an MLE configuration, we can simply turn off the anoxic, simply turn off aeration in CSTR1 and CSTR2 and make it anoxic. So I'm going to add a combiner. All right. So this pump flow will go back. Okay, so we have updated our configuration, made it more plug flow, and also added an option to make it an MLE configuration when we evaluate the process. I'm going to go to the tools. In the tools, because we have SRT calculation, now I need to update the SRT calculation. So I'm going to drag the other CSTRs to the numerator. I do not need to make any change in the yield because my yield calculation still remains the same. But what I'm going to do is I'm going to add sum of variables. So I'm going to add up actual oxygen requirement for all of the tanks so I can monitor the total oxygen uptake of the system or total oxygen demand of the system. And I'm going to do that by summing of the variables and dragging all the CSTRs to the bottom. And on the left-hand side, I'm going to go to custom and then specify AOR. And these symbols can be identified from the output window in SUMO as well. And I'm going to rename this to call it AOR. One more thing I'm going to do is I'm going to look at the ammonia removal efficiency. So in this case, again, I'm going to click on advanced ratio. I'm going to drag the effluent of the primary clarifier, the effluent of the secondary clarifier, divided by what's coming into the system, which is the effluent of the primary clarifier. And on the left-hand side, I'm going to choose to do the same calculation, but with TKN this time, the mass of TKN coming in. So this will allow me to calculate the ammonia removal efficiency. So I'm going to change this name and call it ammonia removal efficiency. All right. Let's go to the input. I want to make sure that the total volume of the system is 2.6 mgd, 2.6 million gallons. So I'm going to divide 2.6 by 4. So that's 0.65 million gallons. And I'm going to split the total volume between 0.65. So just by selecting all the reactors, I'm able to change the volume, the total volume of each of the tanks. Now the total volume is 2.6 million gallons, same as before. So nothing changed. The SRT is the same. The total volume is the same. The only thing which has changed is I've made it more plug flow. What I'm also going to do is I'm going to make sure my internal recycle is 0 so that there is no impact of internal recycle on any of the operations. I'm going to go to output. And this time I'm going to add to the actual oxygen requirement, the total actual oxygen requirement. So going back to the plant by clicking on this plant wide button, other variables, plant, and that's the AOR, that's the total AOR. I'm going to add the ammonia removal to the system as well. All right. Okay, now let me go to the simulate, advanced. I have my SRT calculated, and my SRT is ranging from 3 days to 8 days of SRT. At 12 degrees Celsius, I'm going to press steady state again. So on my x-axis, I have SRT. On my y-axis, I'm looking at ammonia. You can see as the SRT increases, the ammonia starts to go down, nitrate starts to go up. If I look at my ammonia removal efficiency, the ammonia removal efficiency starts up high because the baseline is related to synthesis of biomass. So that is ammonia being consumed for bacterial growth. And then as the SRT increases, the ammonia removal efficiency also reaches above 90%. And that's because of nitrification. If I look at my aeration demand or actual oxygen demand, the green line which showed up is the sum of total. And it has a similar pattern. Now, if we were to compare our ammonia in the effluent to the simulation which we did before, you can see that, as I pointed out before, that the ammonia to reach 1 milligram nitrogen per liter, it's almost the SRT is close to 7.8 days for a temperature of 12 degrees Celsius. But if we revisit this, you can see that it achieves close to 1 milligram nitrogen per liter of ammonia with an SRT of less than 5 days. Okay, so what changed? We did not change the volumes of the tanks. We did not increase or decrease the load to the system. We did not change the temperature. But by making the hydraulics, by changing the hydraulics of the system, by making the reactor more plug flow, we are now able to achieve the same amount of ammonia by operating at smaller SRTs, right? And of course, this allows a lot of flexibility in operations. It allows you to change, let's say, the DO set points in each of the tank, make it more, depending on how you want to set the DO set points, staging the DO set point from high to low, you can try to achieve your effluent target, minimizing your energy demand or optimizing your process during that process, right? So that's the whole objective. And now we are able to compare between different operational settings. Okay, so what's the next step? So the next step for us was to convert this into an MLE configuration. But before I convert it into MLE, I want to save this report as well. So I'm gonna click on this Excel file. I'm gonna name this plug flow. I'm gonna open this report as well while I go back to SUMO and then go back to tools. All right. Now, if we talk about MLE process, the nitrified mixed liquor is actually brought back to the head of the reactor, right? And the internal recycle, what this is called, is proportional to the influent. It ranges from 50% of your influent to 400% or more to your influent. And that has a direct impact on the nitrogen removal. So what we're going to do is we're going to make another controller called proportional flow dependency, and we're going to drag the internal recycle pump, which is this, to the left-hand side of this equation, make it proportional to the influent. So similar to SRT, now we will be able to tell the model that control this flow to 50% of the influent, or 100% of the influent, or 400% of the influent. Let's go to the input tab. And how do you identify where that equation is? It's that button right there. So if you click on this button in your drawing board, you should be able to see that that's the flow proportional dependency which we have just created. You can select that to the advanced window by clicking on this checkbox. But before we move on, we have to convert the first two tanks into anoxic reactors. So we can go to aerobic setting and simply turn the DO set point to 0 for both of the CSTRs. Let's go to the Simulate tab. In the Simulate tab, we already have some of the key parameters which we want to track, as part of the system. So at this point, what I'm going to do is I'm going to repeat this exercise before I look at the impact of internal recycle. So I'm going to turn off the internal recycle to 0%. So there is no change in the internal recycle. Or maybe I'm going to give, let's say, 100% of internal recycle. I'm going to repeat this exercise where I'm going to press steady state and evaluate the impact of SRT. So let's see what happens to our effluent ammonia concentration. So what we have essentially done is we have converted 2 of our existing tanks into anoxic zones for denitrification. But we must understand the impact of that when we are evaluating the minimum SRT and its impact on the effluent ammonia. So you can see that the ammonia concentration, what did we identify? That the ammonia dropped below 1 milligram nitrogen per liter when we were close to 5 days of SRT. However, in this simulation, all we have done is converted 2 of our tanks into anoxic zones. We don't see ammonia dropping below whatever that value of 15 milligram per liter nitrogen is. So the question is why? So, and even at 8 days of SRT, you can see that the ammonia doesn't go much down. So the question is why? And at this point, we'll conduct a quick poll to kind of get the idea from audience. So Erica, if you want to pull up the poll, please go ahead. Okay, so in this poll, what we want to look at is we did not change anything apart from, we did not change any volume. We just made 2 of the tanks anoxic. So the question is why why don't we see ammonia removal in this case? Yep, I am glad to see the direction the answers are going into. We're just going to wait a little more and then we'll continue. Okay. Yep. I mean, as we can already see, the answer is in front of us. And most of us got it right. Majority of us got it right, right? So by changing the two tanks into anoxic reactors, we actually cut down the SRT into half, right? So if we want to reevaluate, or for this process configuration at 12 degrees Celsius, if we want to share results. Oh, yes, I apologize. So you can see the results here, and I'm gonna cancel the poll. So what is the solution? So the solution is essentially to double the SRT whenever our anoxic zones are, some of our aerobic reactors are converted into anoxic zones, right? So I'm gonna change my maximum SRT instead of 8 days, I'm gonna change it to 16 days. Not 816, but 16. And then I'm gonna redo this simulation. And now what you'll see is that the aerobic SRT required for nitrification is a more important parameter to keep track of whenever we are doing these kind of analysis, right? And now you see it takes, for the same plant, it's taking close to almost 13 days, I would say, of SRT to meet an effluent ammonia requirement of 1 milligram nitrogen per liter. Okay, what else do we see? We see when the ammonia concentration is high, the total nitrogen is high. When the ammonia drops below, nitrate pulls up, and that's when we start to see denitrification happening. So for denitrification, nitrification is a prerequisite, right? That's an important consideration to keep in mind. What about our actual oxygen requirement? I'm sure the total actual oxygen requirement decreased by almost 15 or 18%. If I can just pull up the previous example which we did, you can see that in this case, we are reaching towards the end, the actual oxygen requirement is close to 10,000 pounds per day. But if we revisit the latest configuration, it's less than 10,000 compared to the previous SRT set point which we have, right? So we can see that there is a savings when we are looking at a nitrogen removal plant. We can do the same analysis with ammonia removal and so on. But this gives you an idea of how you can put together different configurations, different operational set points, different design strategies, and evaluate the performance of the plant. Okay. One last thing we wanted to do before we go back to our slide deck is to evaluate the impact of internal recycle on nitrogen removal. So now we have identified that the SRT of 13 days is probably enough. So I'm going to change the SRT to 13 days, uncheck this button because I no longer want to evaluate SRT on my x-axis. I want to evaluate my internal recycle. So I'm going to change the internal recycle from 50% to, let's say, 400%. And I want SUMO to do 10 simulations so I can look at its impact on the nitrate in the effluent. And I'm going to press steady state. And now instead of sludge retention time, I have the internal recycle. So SUMO is doing 10 simulations and creating a relationship between the effluent nitrogen parameters and looking at your internal recycle. So you can see that impact of, as the internal recycle increases, so does your denitrification performance. Your total nitrogen goes from 10 milligram nitrogen per liter, 10.7 milligram nitrogen per liter to almost 6 milligram nitrogen per liter due to the internal recycle, increase in internal recycle. Of course, that has some impact on the ammonia in the effluent as well, going through the system. So it allows you to kind of evaluate different operational setting, different design parameters from a full plant perspective. Okay. All right. So I'm going to save this configuration as well. I'm going to call this AS3. By the way, I'm going to share all these with the attendees if they are interested in evaluating it themselves. And I'm going to write a report for this as well. Okay. This time, I'm not going to open the report. And I'm going to go back to my slide deck. All right. So we looked at how to set up a configuration in SUMO. We looked at impact of different operational parameters on our effluent quality, our sludge yield, our oxygen demand. But how does it link to the model matrix itself? What does the model matrix look like? Because SUMO has an open process code, meaning that you can actually go into SUMO and look at what one-step nitrification denitrification model is. You can look at what the two-step nitrification denitrification model is. You can follow the stoichiometry. You can follow the rate of reactions. So it's important to understand how the Guyer matrix actually works and how does that link to understanding of your operations and design. Okay, so with this simple example, my goal is to explain what the stoichiometry and the rate of the reaction come from. Okay, so let's imagine there are two reactions in the matrix. One is aerobic growth of heterotrophs, and the second is decay of heterotrophs. There is always substrate involved when we are talking about aerobic growth of heterotrophs. What does it happen on? So it's soluble substrate. So there is a yield associated with that. Minus means something is being consumed. And if you follow the same idea, a positive means that something is being generated. So a soluble substrate is removed, oxygen is being consumed, ammonia is consumed, and biomass is generated. So that's how the stoichiometric relationship works when we are looking at Guyer matrix. Decay, on the other hand, means that the biomass disappears, generating a particular biodegradable substrate and and generating COD, which is not biodegradable or not at least easily biodegradable. Now, this is a simple example. And all of those stoichiometry is then multiplied by the rate equation. And what is your rate equation? So your rate equation is essentially your maximum specific growth rate, if we are talking about the aerobic growth of heterotrophs, multiplied by a bunch of mathematical functions, multiplied by the biomass concentration, right? So that's how you can write it as being simplified. What are functions? Now, these functions can be monosaturation terms, switching functions, which we'll look at in our next slide, but they can depend on soluble COD substrate concentration. It depends on your rate equation, depends on your oxygen concentration. The rate equation depends on the ammonia concentration, which is available in your solution. So to simplify the rates, let's look at just one single example. We call it MSAT. It's basically a monode saturation term, where the substrate concentration is divided by the half saturation value plus the substrate concentration. If you look at this chart right here, as the substrate concentration increases, now it could be ammonia, it could be dissolved oxygen, it could be soluble COD. As the substrate concentration increases, the rate of reaction also increases. And beyond half saturation value, so the half saturation is the concentration of your substrate at which the rate of reaction is 50%, okay? And up to your half saturation value, the rate is a first order where minor changes in the substrate concentration proportionally increases your rate. And after that, it becomes a zero order relationship. Now, how does this help us understand the operation of, let's say, nitrification process? So for nitrification, let's say our half saturation value is 0.25 milligram oxygen per liter. So is there a point of operating a facility more than 2 milligram of oxygen per liter because our rate of reaction will be maxed out at 2 milligram per liter? No, you're just spending more aeration energy. So that's how you will use these functions to kind of understand the operation. There are more than monosaturation terms such as switching function, which affects DO inhibition and denitrification, bell curve, which affects your pH, and then Arrhenius, which impacts your temperature, okay? So this is an example of nitrification rate equation from our one-step nitrification denitrification model. I understand it looks a bit terrifying, but if you simplify this, that's the maximum specific growth rate, which is temperature corrected. Then that's your biomass concentration. That's related to the sludge retention time. Ammonia, oxygen, bicarb, which is important substrate for nitrification, oxygen, essential nutrients, and then impact of pH, right? So all of these equations or functions are multiplied by each other and help us determine if the nitrification reaction will be active or not active. So let's look at three examples. The first one, when nothing is limiting, what happens? Of course, 0.9 is your growth rate temperature corrected at 20 degrees Celsius. 100 here specifies that you have enough SRT. And then all of your functions are close to maxing out. So nothing is limiting. But what if you set your aerobic tank to 2.25 milligram per liter of oxygen? That's your half saturation. So what will happen in that case? Or if you decrease the SRT of your tank and the temperature happens to be 10 degrees Celsius, what would happen in that case, right? In the first case, your rate of reaction will become close to 50% for the DO monosaturation term. In the second case, your growth rate will be inhibited and you have less biomass because of smaller SRT, right? So that will be driving your nitrification rate down. So this equation can help you understand the changes you can make in operation that impacts your nitrification and how to take best advantage of the situation, right? Okay, so this was a brief overview of how to use SUMO, how to link it back to rates and understand the impact of operation. For universities and researchers, how you can use this In teaching, you can use it for design and operation. If AEESP university members might be eligible for some discounted student licenses for teaching semester, for their teaching semesters, if that's what you want to do. Researchers, on the other hand, can use it for batch testing, identifying kinetics, stoichiometric parameters, running pilots, even develop models in SUMO, because you can actually go and see how the models are built. And at this point, I would recommend look at the documents which are shared, and you'll be able to see how it can best support your efforts. All right. Kara, back to you.
Wow, thank you so much. So I encourage everyone online to applaud. You can use the in the chat function, you can add your gratitude for this really informative seminar. There's lots and lots of questions. So I'm going to try to touch on questions that I think will be of the greatest interest to the greatest number of participants. So one of them is, can SUMO simulate dynamic influent quality? So you gave us great examples of, I guess a fixed quality influent.
Yes.
Can you explain a little bit about dynamic simulation mode?
Yes. So you can actually set up influent dynamic, a dynamic table. You can change your flow dynamically, COD, TKN, temperature, and a lot of these operational inputs which you see when you go to the input tab, such as dissolve oxygen set points, they can be changed dynamically as well, right? Today, the focus was to briefly introduce everybody to steady state and understand impact of different operational conditions. Yeah, but it is possible.
Yeah, and you covered a tremendous amount. I'm very impressed. If I could cover that much in one of my lectures, I'd be feeling very accomplished. Another question is, you walked us through, I think the examples you gave show how customizable the software is. I'm curious if there are like packages that have like pre-configured configurations for common nutrient removal processes, or even some of the more innovative, treatment processes that are available.
Yeah. So as I showed in the beginning, so when you open SUMO for the first time in the home page, there are tons and tons of examples, including full configurations where you can do nutrient removal and recovery as well. And so I would recommend download, install SUMO, and then go through that list and see if there is something which you find you don't see, you can always write to us and we'll give you an example. We'll build you an example.
Amazing. Another question, does SUMO have the ability to calculate gaseous emissions? And of course, the greatest interest would be in greenhouse gases.
Yes. So we do have a model called SUMO 4N. So SUMO 1 is a one-step model. SUMO 4N is actually 4 steps, and those 4 steps are related to nitrification and denitrification. So you can see nitric acid and nitrous oxide being produced in the system under different operational conditions. And then, yes, we do have a very good gas transfer model.
This is one I'm sure you must get in your role a lot at Dynamita, is given that there are other options besides SUMO, like BioWin, GPSX, can you share a little bit about the benefits or the trade-offs between the commonly used models?
Yeah, I believe a lot of times if you look at general models such as SUMO 1 or SUMO 2 or two-step nitrification, denitrification models, they are quite, if I don't want to say same, but they are similar among packages. And then a lot of the functionalities can be similar, right? A lot of times what it comes down to is how easily you can configure, how easily you can get the outputs out, and what you're comfortable with, I would say. But I mean, because I can't speak for other softwares, I can just tell you how we can help you remove doubts from your design or operation. It's focused on, so we're trying to standardize it for our industry so that everybody can pick that up. Yeah.
Wonderful. All right, so we are coming up on time. I want to conclude by thanking you again very much for an extremely informative seminar, and thank Dynamita for participating in this new webinar series that AWSP is offering. And a reminder to all of our attendees that the recording of today's webinar will be posted on our YouTube channel, and so you will receive an update by email because you registered when that is available. So I'm sure many people will end up going back to the recording because you covered so much and it was extremely informative. And also, Tanush will do his very best to follow up with other questions that we were not able to get to today. Thank you so much, everyone, for joining us.
Yeah, thank you.
Enjoy the rest of your day.